In a previous video, I explained the field structure in the set of real numbers and commented that an identical structure can be created in other sets. I also claimed that this structure is really an algebra, but due to the simplicity of the real numbers, the structure is buried under the field structure. In this video, I will continue my presentation, and I will delve deeper into algebraic structures, where algebraic here means any structure built in a set, not just that of an algebra. The mathematical area of abstract algebra studies all such structures. I will take things from the beginning and slowly build my way to the structure of an algebra. To understand the depth of an algebra, we will have to understand a series of other related structures which come before it. Each structure leads to interesting results. In this video, I will assume that the viewer has already seen the previous one, and there is an elementary familiarity with the topic. So, I will use formal language and notation, although at an elementary level. Are you ready? Let's start with the most basic concept in mathematics. The concept of a set. A set is a collection of objects, usually having a property, but there is no other relation among themselves. The members of a set are called elements. To build an algebraic structure in a set S, we introduce functions. A function with domain, the Cartesian product S cross S, and target set the set S, is called a binary operation in S. Binary since the input is a pair of elements, and operation since it operates on the two elements to get the image. Instead of the standard function notation, we prefer to indicate binary operations with a symbol between the two elements of the pre-image. For example, if the star symbol is used to denote the binary operation, we write the image of two elements x and y as x star y. Often, the image x star y is called the composition of x and y. Now I can give you a formal definition of an algebraic structure. An algebraic structure is an ordered n-plet of set S and n-1 binary operations on it. In the most popular applications, we almost never have structures with more than two binary operations. The curious reader may also question why only binary operations are used. One can easily introduce unary, ternary, etc. operations. The response is like the previous comment. In the most popular applications, only binary operations are encountered. It's very common to link algebraic structures. Given two structures, one on the set S and another on the set T, a linking requires a function that takes elements from S and T and maps the pair to elements of S or T, or even another set having another structure. This is still a binary operation since the input is two elements. However, the domain is formed from more than one set. So, I will call it an external operation as opposed to the previously defined internal binary operations where the two elements of the same set are mapped to a third element of the same set too. A random binary operation is not that exciting for mathematics. Hence, we are interested in binary operations that exhibit certain properties. The following list provides the 4 properties that we are going to need. They are known to you from standard arithmetic, except that the properties now refer to any abstract binary operation. For the description of the properties, I will indicate the binary operation by a star and the set by S. Property 1. We say that the binary operation in S is associative if the result of the composition of 3 elements is the same independently of left to right or right to left computation. Property 2. We say that a binary operation in S is commutative if the result of the composition of 2 elements is the same independently of the order of the 2 elements. Property 3. We say that the binary operation in S has a left neutral element if there is an element E such that E star X is equal to X for all X in S. Similarly, E is a right neutral element if X star E is equal to X for all X in S. The element E is called neutral if it is both left and right neutral. It is easy to see that if an operation has a neutral element, then it must be unique. Say that E prime is a second neutral element. Then, E star E prime equals E prime since E is a neutral element, and E star E prime equals E since E prime is a neutral element. The left-hand sides of the last 2 equations are equal. Therefore, the right-hand sides must also be equal. That is, E is equal to E prime. Property 4. If the binary operation has a neutral element, we say that x prime is a left symmetric element of x, if x prime star x is equal to e. Similarly, x prime is a right symmetric element of x, if x star x prime is equal to e. The element x prime is called symmetric of x, if it is both left and right symmetric. Now here are some comments on the terminology. Another name used for the neutral element is identity element. Another name used for the symmetric elements is inverse elements. Abstract algebra is guided by our experience with the real numbers. Hence, mathematicians tend to classify the operations as additive or multiplicative. When mathematicians think of the operation as additive, they rename the neutral element as the zero element and the symmetric elements as the opposite elements. When they think of the operation as multiplicative, they rename the neutral element as the unit element and the symmetric elements as the reciprocal elements. Even if one wants to keep the terminology general, it is impossible since the standard terms from addition and multiplication have already been incorporated in some definitions of abstract algebra. I want my viewers to get used to the ideas of the abstract language without their mind being stuck to addition and multiplication. So, I will try to maintain full generality unless the actual definitions use the standard language. The previous properties can be fully appreciated by a few examples. Example 1. On the set of real numbers, with the help of the standard operations of addition and multiplication, we define the star operation between x and y as seen on the screen. This operation is obviously not commutative since the two elements x and y enter in the calculation in an asymmetric way. It's not associative either. Let's check this. For any real numbers x, y, and z we have However, the star operation has a neutral element, and it is the zero number. Now, let x prime be the right inverse of x. Using the definition, x star x prime equals 0, x prime satisfies a linear equation. This equation is solved easily to express x prime in terms of x. From this result, we conclude that every element has a right inverse element with respect to star. Let now x double prime be a left inverse of x. Then, using the definition, x double prime star x equals 0, x double prime satisfies a quadratic equation. If x equals 0, then x double prime equals 0, and it is equal to the right inverse. Hence, the neutral element is its own inverse element, as it should be. If x is not 0, the quadratic equation can be solved in the set of real numbers if its discriminant is non-negative. Therefore, left inverses exist only for those x whose square is less or equal to 1/4. In fact, the quadratic equation provides two solutions. You can easily check that both solutions are acceptable. It takes a little additional work to verify that the right and left inverses do not coincide for any non-zero real number. Indeed, if for any number x the two coincide, then the following must be valid. We can leave only the square root on the left-hand side and then square the result to find an equation that contains only x squared. Finally, cross-multiply to reduce this equation to a polynomial 1. In the set of real numbers, the last equation has only one solution, x equals 0. Hence, for no other number the right and left inverses are equal. Example 2. Given a set S, let P of S be the set that contains all possible subsets of S, which is known as the power set of S. The four examples that follow discuss operations defined in the power set. Elements belonging to the power set are indicated by capital letters, while elements belonging to the sets of the power set are indicated by lowercase letters. Case 1. In the power set, we introduce the intersection of two sets X and Y. Often, operations between sets are shown diagrammatically to help our intuition and calculations. If the set S is represented by a rectangular area, a subset is represented by an area inside the rectangle. Then, the common area of any two sets is their intersection. The operation is automatically commutative since the two sets enter in a symmetric way in the definition of the operation. It's also associative. This can be verified very fast using the geogrammatical representation of the operation. The operation has a neutral element, which is the set S. The set S is its own inverse. Besides the neutral element, no other set has an inverse. To see this, let X be a proper subset of S. A proper subset is a set that has at least one element less than S. If X prime is the inverse of X, then the intersection of X prime and X must be equal to S. However, this is not possible since X is a proper subset of S and the intersection will result in a proper subset of S. Case 2. We equip the power set with the union of two sets. This operation is shown graphically in the figure. The colored area is the union of the two sets. The operation is automatically commutative since the two sets enter in a symmetric way in the definition of the operation. It's also associative, which can be checked easily diagrammatically. The operation has a neutral element, which is the empty set. Besides the neutral element, no other set has an inverse since the union of a non-empty set with any set cannot be empty. Case 3. We equip the power set with the difference of sets. This operation is shown graphically in the figure. The colored area is the difference x minus y of the two sets x and y. The operation is not commutative since the two sets enter in an asymmetric way in the definition of the operation. It's also non-associative, which can be checked diagrammatically. The empty set is a right neutral element. However, there is not a left neutral element. If E was the left neutral, then E minus x should be equal to x for all sets x. But E minus x does not include any of the elements of x. Hence, it cannot be equal to x if x is non-empty. Consequently, the difference of sets has no neutral element. Case 4. We equip the power set with the symmetric difference of sets. Given two sets x and y, the symmetric difference of the sets is the union of the differences x minus y and y minus x. Equivalently, the symmetric difference is the difference between the union of the two sets and their intersection. This operation is shown graphically in the figure. The colored area is the symmetric difference of the two sets. There are a handful of symbols that mathematicians use to indicate the symmetric difference. Among them, I chose the O+, which is reminiscent of the standard addition of numbers since the symmetric difference has similar properties, and it is considered an additive operation. The operation is automatically commutative since the two sets enter in a symmetric way in its definition. It's also associative, a claim that can be checked fast diagrammatically. The operation has a neutral element, which is the empty set, and each set acts as its own inverse. To stress the similarity with the addition of numbers, we can indicate the inverse element of set x by O minus x. Then, O minus x equals x. This equality is equivalent to x O plus x equals the empty set, which is required by the definition of the symmetric difference. We are ready now to name the algebraic structures. Mathematicians use the names such that they do not have to repeat all underlying properties every time they use one of these structures. A set S endowed with a binary operation is called semigroup if the operation is associative, monoid if the operation is associative and has a neutral element, group if the operation is associative, it has a neutral element, and all elements have inverses. If the operation is also commutative, then we add the adjective abelian or commutative. Hence, the previous list is expanded by the addition of another three structures: abelian semigroup, abelian monoid, abelian group. Adding properties makes the structure tighter, which I indicated in my diagram with an inverted triangle. A tighter structure implies more relations among the elements. A more loose structure allows more freedom for the elements, but it is also a more boring structure. It is evident that if a theorem is proved for a particular structure, then the theorem remains true for any other structure that has additional properties. Here is our first theorem. In a group, the inverse of an element is unique. To prove it, let x prime and x double prime be two inverses of x. Now, let's take the equation x star x prime equals z and compose it with x double prime from the left. The right-hand side is x double prime. Using associativity, the left-hand side is equal to x prime. Therefore, x prime equals x double prime, and there's only one inverse. Our second theorem is, in a group, the equation b star x equals c has a unique solution for x. To prove it, let b prime be the inverse of b. Then, we compose the given equation from the left with b prime. Using associativity, the left-hand side is equal to x. Therefore, the equation has the unique solution, x equals b prime star c. Said in another way, the theorem we just proved states that, in a group, an element is always cancelable from one side of an equation. When it is canceled, its inverse appears on the other side. This is exactly what we do for addition and multiplication. However, we must be careful with the order of the elements if the group is not abelian. Look at the following equation, and first cancel the element d, then the element b from the left-hand side. Now, imagine the product, d star b, as one number and remove it from the left side. Therefore, by comparing the two ways to solve the equation, we have proved that the inverse element of x star y is the composition of the inverses x prime and y prime in reverse order. I will list a few examples of the structures mentioned above. Example 1. Let n be the set of natural numbers, and n asterisk the set of non-zero natural numbers. Then, n asterisk equipped with the operation of addition is an abelian semigroup since addition is associative and commutative. However, it is not a monoid since it does not contain the zero number. On the other hand, n equipped with the operation of addition is an abelian monoid, but the elements do not have opposites. Example 2. Let z be the set of integers, and z asterisk the set of non-zero integers. The operation of addition is not well defined in z asterisk, since there are pairs of integers that add to a number that does not exist in z. On the other hand, z equipped with the operation of addition is an abelian group. Let's also look at the operation of multiplication. In this case, both sets, z and z asterisk, are abelian monoids since they both contain the unit element. However, none of them contain reciprocal elements. To handle this, we extend the set of integers to the set of rational numbers q. Then q equipped with the operation of addition is an abelian group. However, q equipped with the operation of multiplication is still not a group since the zero does not have a reciprocal. If the zero number is excluded, q asterisk equipped with multiplication becomes an abelian group. Example 3. Recall that the intersection and union operations between sets are associative, commutative, and they have a neutral element. Hence, the power set of a set S endowed with the intersection or union of sets is an abelian monoid. Example 4. Recall that the symmetric difference between sets is associative, commutative, and has a neutral element. In addition, each set has an inverse with respect to this operation. Hence, the power set of a set endowed with the symmetric difference of sets is an abelian group. Example 5. This example relates to geometry. Consider the set D4 that contains the symmetries of a square. These are rotations and reflections. More precisely, the square may be rotated about its center by 0 degrees, 90 degrees, 180 degrees, and 270 degrees. Notice that a rotation by 360 degrees is identical to a rotation by 0 degrees. It can also be reflected about its horizontal axis, its vertical axis, and its two diagonals. We now endow the set D4 with the operation of map composition. Then, it is a matter of straightforward calculations to check that D4 acquires a group structure. The resulting group is known as the dihedral group. However, it is not a abelian group. For example, a reflection across the vertical axis followed by a 90-degree rotation results to a different element than a 90-degree rotation followed by a vertical reflection. Consulting the figure, the first composition equals the reflection about the first diagonal, while the second composition equals the reflection about the second diagonal. In order not to make the video very long, I will finish it at this point. I will discuss algebraic structures with 2 operations in a forthcoming video. I hope you liked this presentation. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.